Hello and welcome again to my Physics Online video lecture series. In today's video we're going to be talking about a charged particle in a magnetic field. So the main things that we can look back upon from previous videos and recall are that we had electric fields which told us force per unit charge, such that F sub E is given by the charge times the electric field at that point in space. And I suppose we could add to that electric fields it can be represented using field lines which originate on positive charges and then terminate on negative charges. E-field lines can be open, that is, they can have an origin point without any particular termination point, meaning they just stretch to infinity, or they can terminate at some point or set of points in space without any origin in space because they originate infinitely far away. I think that those are kind of the main things to say about E-fields. So you might have an E-field that looks like this at some region in space, and then if you happen to have a charge Q located in that same region of space, then the force acting on that charge will point along the E-field line such that F sub E is Q times E. Magnetic fields can be contrasted with electric fields in sort of two ways. First of all, they behave in a similar way to electric fields in that they are telling us something about force per unit charge. It's just that there's more to it than just field times charge gives you force. One more thing to be said about the electric field is that its magnitude has units of newtons per coulomb or volts. So having recalled these things, let's consider magnetic fields in some sense by way of contrast. So a little bit of comparison and contrast here. The first thing that we can say about magnetic fields by way of contrast is that although they can still be represented by field lines, the field lines for magnetic fields tend to be closed rather than open. So E-field lines are open and they're not allowed to cross each other. B-field lines are closed. So, in other words, this right here might be a perfectly fine B-field line, even though it's not generally going to be a typical E-field line. So B might look like this. E, you have a positive charge, and the field lines just kind of radiate out from that positive charge, like so. And in fact, if I have two E-fields, I get a dipole. So with magnetic fields, there are no monopoles, whereas for electric fields there are. This right here would represent an electric monopole, specifically a positive electric monopole. There can be a negative one like an electron. For magnetic fields, there isn't really such a thing that we know of as a magnetic monopole. Electric field for a dipole would be like a plus and a minus charge combined, and what you end up getting is a field that looks basically like this. Out here you end up having field lines like so and like so. So this would be my electric dipole, positive charge on one side, negative charge on the other side. For the magnet, you have a north and a south pole, and so the magnetic field for a dipole actually looks kind of like the electric field for an electric dipole, where the north pole is the origin and the south pole the termination. The difference is that with magnetic fields, you can't just have a north pole, nor just a south pole. So this is sort of not allowed. They always kind of are together. If you cut this magnet in half, you get two new magnets, each of which has a north pole and a south pole. Okay. The unit for the magnetic field is the Tesla. However, we also very often use the CGS unit, which is the Gauss. And the conversion is that 1 Gauss is 10 to the minus 4 Tesla. Now, why do we use the CGS unit here as opposed to the MKS unit? Well, for calculation purposes, we probably don't, or we should convert over to Tesla. So, in some sense, this one right here is the unit that you need to ultimately be working in. But the Gauss is 4 orders of magnitude smaller, is useful because the Earth's magnetic field is on the order of half a Gauss, which is on the order of 5 times 10 to the minus 5 Tesla. So a lot of common magnet fields tend to be in Gauss, because if you use like a decent play with it at home bar magnet, you're probably on the order of tens or maybe hundreds of Gauss, but that's still like 10 to the minus 3, maybe even 10 to the minus 4, 10 to the minus 2, something like that Tesla. A very strong magnet for messing around with at home would be maybe 100 Gauss. More likely you have like 10 or so Gauss. Last but not least in this by way of contrast, what about force? So if you go back to electric field, recall that the force is just Q times E. With magnetic field, the magnetic force is actually given by a cross product. It's QV cross B, where V is the velocity that the charged particle is moving at, and then B is your magnetic field. So we actually use a B for magnetic field. Worth remembering is that if you want to figure out magnitude and direction for a cross product, the magnitude will be given by the magnitude of the vectors involved, so QVB times the sine of whatever angle is between the two vectors in the cross product. And then the direction, what you do is use what's called the right-hand rule. The resultant will always be perpendicular to each of the two vectors involved. And so it's perpendicular to QV and it's perpendicular to B. The right-hand rule, again, take your fingers of your right hand, point your index finger in the direction of the first vector, point your middle finger in the direction of the second vector, however they may be oriented, and then your thumb will give the direction of the resulting vector. So that's just figuring out the magnitude if you know the magnitudes of the vectors involved. There's actually a second trick that you can use. You know that it's going to be perpendicular to these two, which also means it's going to point up or down in the plane containing the two vectors. And essentially the sine of this angle will tend to be positive as long as the angle is between 0 and 180, and it will be negative if it's between 180 and 270. So if I happen to have V or QV in this direction, and then B is off in this direction, this right here would represent my angle phi. It's always counterclockwise from the first vector in the cross product, the QV in this case, to the second vector, the B. And so you can look and see, is it positive or negative? If the sine of the angle is positive, then if you're looking down at this page that has the two vectors in it, then the force vector will point straight up out of the page at you. And if the sign of the angle is negative, then the vector actually points down away from you through the page. Same works for the screen. If you're looking at the screen here, and we've got this vector and this vector, if sine of phi is positive, then FB will point out of the page towards you. And if it's negative, then FB will actually point into the page away from you. So if we draw for this one, this actually ends up being negative. So in this case, we would actually draw FB pointing into the page away from us. Another reminder with cross products, you can do them using unit vectors. One way to do that with the unit vectors is to set up a matrix and find the determinant. And basically your matrix for whose determinant you are finding will look like this matrix that I've drawn here, where you have I hat, j hat, k hat in the top row. The second row will have the x, y, and z components of the first vector, which in this case is qv. And then the bottom row, the third row, has the x, y, z components of the second vector, b in this case. And so your determinant is basically this sum. So qvx by minus qvy bx times k hat. qvy bz minus qvz by I hat. And plus qvz bx minus qvx bz j hat. That gets you your cross product of this particular set of vectors. So that is how much force we're finding. Going back to the question of the units, so coming back up here, we said units are Tesla. Looking at this way the force is set up, 1 Tesla times 1 Coulomb meter per second gives you a force of 1 Newton. Put differently, the unit of Tesla is equivalent to Newton times second divided by Coulomb times meter. So that gives you what a Tesla is. All in all, the larger the charge, the faster the particle, and the larger the magnetic field, and the greater the angle, or more nearly 90 degrees, the angle is between the velocity and the magnetic field, the greater the amount of force. So that's a bunch of different factors all at once. So let's do a short example. We've got a particle of 1.5 nanocoulombs, It's got a velocity given by this vector interacting with a magnetic field given by this vector. We want to know how much force. We want to know what the force is. So F is going to be equal to QV cross B. So I'm just going to set up the matrix. You can, of course, jump to the formula here if you'd like. So I hat, j hat, k hat, qvx, qvy, qvz, bx, by, bz. This gives the following vector sum, which when added together gives a force of 1.2 times 10 to the minus 11 newtons I hat minus 1.8 times 10 to the minus 11 newtons j hat. If we wanted to instead express this as a magnitude, we would have to basically dot this vector with itself and then take the square root of that dot product. For what it's worth, this vector can be rewritten in terms of I hats and j hats as negative 1.2 I hat plus 1.8 j hat times 10 to the minus 11 newtons. So if what we want is the magnitude of the vector, then we could write this as f is equal to square root of f dot f. And so you're now taking the square root of negative 1.2 I hat plus 1.8 j hat times 10 to the minus 11 newtons, dotted with the same. So negative 1.2 I hat plus 1.8 j hat times 10 to the minus 11 newtons. Now the times 10 to the minus 11 newtons can just be pulled straight out of the square root. And so F ends up just being the square root of, and also the negatives sort of cancel. So you just have 1.2 I hat plus 1.8 j hat dotted with 1.2 I hat plus 1.8 j hat. And then that is all times 10 to the minus 11 newtons, which is not under the square root. So if you were to put this into your calculator, 1.2 times 1.2 should be 1.44. And then you're adding to it 1.8 times 1.8. That gives you 4.68 total. If you take the square root, you get basically 2.16. So the total force, if you want just the magnitude, is about 2.2 times 10 to the minus 11 newtons. And if you want the direction, then you can always just divide the force by the magnitude of the force. And so what that ends up looking like is negative of 1.2 I hat plus 1.8 j hat divided by 2.2. All the times 10 to the minus 11 newtons parts will cancel. And so this is properly the direction in unit vectors. You could also figure it out in terms of an angle counterclockwise from positive x, although that's going to be a little bit sillier to do if we had a vector that actually had an I hat, j hat, k hat in it. This one happens to be in the xy plane, so you could do a vector direction by using just the angle within the xy plane. For what it's worth, the angle within the xy plane would be about 213.7 degrees. And you can get that by using the tangent of that angle should be negative 1.8 divided by negative 1.2, and then making sure that you're in the correct quadrant. Alright, so that's all for today's video. As always, I hope that you've learned something from it, that you found it helpful, and thanks for watching.